I'd shown this slide at the end of last class, a quick quiz. So I hope you've gone through this. I'd like your inputs, and then we will continue. So any takers? Yeah. So let's go one by one. So let's start with the column under compression. It's a very straightforward thing. Yeah. Yeah. Right. You could just raise your hands if you say yes for that. Yeah. Yeah. So then, what about the panel in pure shear? No. Okay. Let's go to the next one. Shaft in torsion. Can it buckle? No. Yeah, so even before whether it can buckle or not, we just want to know, can it lead to compression, right? So because we're taking that as, let's say, the reason for the buckling, if the compressive load or stress becomes beyond a certain value. So just like to know, will a panel in pure shear, we are in shaft and torsion. So when you have a shaft, let's say a circular shaft, and you're subjecting both ends of it to a torque, right? So, no. Okay. Next, beam in pure bending. Yeah. What is the reason?
When you're bending a beam, one side is going to be in tension, the other side is going to be in compression.
Good. Yeah. Excellent. Yeah. So the other one, beam under concentrated transverse force. So in other words, there's a beam like this. Could be any boundary condition, let's say cantilever or simply supported. The transverse force means that is perpendicular to the length of the beam. So it could be either this way or this way. So is it possible that it could?
Yeah, it's the same thing.
Exactly, same reason, because instead of a pure bending moment, you're having a shear force along with the bending moment. So that's the reason. What about the last one, which is more typical of the aerospace wings, right? Yeah. Okay. So you're right about the first and these three, but in reality, the answer is all of the above. So these two as well. And since that is a little tricky, so I'll just spend a little time on explaining how that really happens. Okay. So let's take the second one. So what is referred to over there is essentially a panel like this. It could be any shape, and it need not be square or rectangle or any particular shape. It could be any shape. And then we typically, by definition, always remember when we say a panel or a plate or a shell, we are essentially saying that one dimension is small compared to the others. In this case, it is the thickness, right? Or what we typically refer to as the height. Okay. So now let's take somewhere in between the origin to define a coordinate system, very similar to the one that we introduced for the strength-based design last time. So we will say that there is x1 and x2. Okay, so this is, let's say, x1 and the unit vector v1. So remember, in my slides I had b in bold, and therefore there was a distinction to make it a vector. Here, instead of wasting my ink rewriting over that, I would put an underline, and this is how typically it's done when we write, either on the whiteboard or in your notes. But when you document it with any software, you typically use a bold letter to denote that it's a vector, right? So similarly, on this side you have x2, b2, and because we typically use what is known as a right-handed rule, so you go b1 cross b2 should give you positive b3. So in other words, it will have b3 in the downward direction, and that's the direction of x3 coordinate along with the unit vector b3. So b1, b2, b3, all of them have magnitude of 1. So we will put all of them together as this way. Okay, so where I is equal to 1, 2 and 3. Those are the numbers, values it takes. Unless otherwise mentioned, or whenever I use Latin letters like I, J, K, L, M, N, etc., they will go through this 3 numbers, 1, 2, 3. Whereas if I use Greek letters like alpha, beta, etc., then they go just 1 and 2, okay, which is what we would eventually want to get to, because we start with a 3-dimensional model, we get to a 2D model for this. So that will be not having your x3 explicitly, it will be integrated in some sense. So only x1 and x2 will remain, only b1 and b2 will remain, and therefore we would just call it b alpha, referring to only b1 and b2. Similarly, x alpha referring to only x1 and x2, right? So that's again, the other notations are similar. Along x1 we will have a length of L, and along x2 we will have a breadth of B. Okay, so now that's as far as the structure itself is concerned, panel. Now we are coming to the load that it is subjected to. Here we are saying it's under pure shear, which means that the external load that is coming onto this system is something that is on the edges in the tangential direction. Okay, so unless and otherwise mentioned, shear refers to in-plane shear as opposed to transverse shear. Transverse shear is involves the thickness coordinate. So it could be on the top surface or bottom surface. In fact, that is much more common in the aerospace engineering, because this could be, let's say, a part of a panel of the entire wing, right? So the wing is typically made, especially if it's made out of metals, many sheet metals which are brought together, riveted, and therefore each one of them is like a panel. And so that's the panel that we are talking about. But here we are talking about in-plane shear, which means that it will be on the x1 face parallel to the x2 direction. And so it will be on this face, for example. What do you think is the positive direction for that? You're familiar with the convention for tau 1, 2? Tau 1, 2. On this face, would it be to the left or to the right? B1 and B2 are?
It's in plane, right?
Yeah, yeah, that's correct, yeah.
So what's the question beyond that?
The question is, in this particular problem, we are saying it's under pure shear. So the only non-zero stresses that are applied externally are tau 1, 2 and tau 2, 1, right? So there's nothing else that is applied. No other stresses are there. So I just want to know, will it take, first of all, does it exist on this face?
No.
No? Does it exist on this face? On the top face?
Yeah.
Okay. So remember that. Anybody agree or disagree with him? Yeah. So Nafis says that these two stresses will be only on the top and also bottom surface.
Yeah.
Yeah, top and bottom surface, not on the edges. Do you agree or disagree?
Well, if you say tau 1, 2, that means
Uh-huh.
it's on the it's perpendicular to the B1 plane.
Exactly,
and it
exactly.
points into the B2.
Very good. Yeah, 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 yeah.
So
So the general notation is, if you have a sigma ij, the first index refers to it acts on a plane, to which bi is the normal. Okay, in other words, if it's if I happens to be 1, then b1 is normal to it,
so
right?
for tau 1, 2, it would point out of the face
Mhm.
that's perpendicular to x1, right? So it's like
Yeah.
a side face.
Yeah,
And it would act in the direction towards x2.
very good. Yeah, so that's right. So essentially it's stress like this, okay, on this face, because you see that the first index refers to the direction to which b1 is there, normal to this particular phase, and therefore I is taken care of. And as you rightly pointed out, it happens to be in the 2 direction, the load itself. So that's the direction of the stress itself, right? So okay, so J happens to be 1 in this case because we're writing 1 and 2, right? So it means that what we have indicated over here is actually tau 1 2, right? And is there any other phase? So remember, this is like a cuboid, so how many phases does it have totally? 6. So we have shown on one phase. Is there any other phase on which tau 1 2 will act?
Tau 1 2. Well, if we do tau 2 1, it'll be on the.
Let's go one by one. Let's not jump to this. Let's stick with tau 1 2 to start with. We have shown it on one of the 6 edges. Is there any? Yes, Ivan.
Other side.
Very good. Other side, you mean this one? Yeah. So because for that also the normal is B1 but in a negative direction, so it's minus B1. So on that phase also it will act in the 2 direction, but which is the convention, you remember, positive tau 1 2, which direction will it act on that phase?
Will also be in the negative direction as well.
Correct, yeah. So because here we have a normal which is in the positive B1, therefore we had this stress in the positive B2 direction, whereas on this edge the normal is along negative B1, and therefore you would have your stress also along the negative B2 direction, right? So if we were to denote that, that would be what it is, and once again that is also tau 1 2.
Do they always counteract?
Come again?
Shear stress is always counteract.
Yeah, absolutely, yeah. But now you see that while the forces will balance out, you will see that it is creating a torque, right? So it's creating a torque about this that has to be balanced, and that's what is the role of your other stress, which we call as these two, we call as complementary. For that matter, your sigma ij and sigma ji are also complementary.
You wrote tau 1 2 over.
Yeah. See, if you can use sigma for all the stresses, or you can use sigma just for the normal stresses and tau for the shear stress. So this is kind of common notation. Either one of them is fine.
So you wrote
As long as the indices are different from each other, you know that it's a shear stress. If the indices are the same, it's repeating index, then it's a normal stress.
so you wrote tau 1 2 like both times. So
Yeah.
It's supposed to be tau 1 2. So then that would mean that the opposites of tau 1 2.
No, remember the notation we had? The first index always points out to what the normal direction is. So for that edge, the normal is parallel to B1, but in the negative sense, so it's minus B1, which is why it is also tau 1. The first subscript is 1. Okay, second subscript is it has to be because the normal is in a negative direction, therefore this force or stress also has to be in the negative direction. So because positive B2 is this way, therefore negative B2 is that way, and that's why that particular direction we have shown, right? So yeah, we have an issue now that if tau 1 2 alone exists on these two edges, then you have unbalanced torque. So in other words, if this were just free, it will just keep on rotating unless and until some other force or stress comes and stops that. Okay, so we are done with 2 of the edges. We said that there are 6 edges to this cuboid. So what about the other 4 edges? Will any one of them will have tau 1 2? No. So those are the only 2 edges which have a normal parallel to the B1 direction, and therefore those are the only ones in which tau 1 2 acts. What about the other stress which is complementary to that, tau 2 1, which are the edges on which it will act?
So it would be on the
Okay.
that phase
Okay.
towards the x-men direction.
Okay, very good. So this is an example of that, where, as you said, it's on a phase into which B2 is the normal, and the action of the stress itself will be along the B1 direction. Now this is a positive B2, and therefore it has to be along the positive B1 direction. So this is how it would be. Okay, so remember, this is tau 21, right? Any other phase on which it acts?
And also the opposite
Yeah.
phase will go in the opposite.
So the same logic like we did last time, but it would be in the opposite direction, because that's the negative direction of B1. So that would once again be tau 21, right? It's better not to write in the interior so that you don't get confused. Okay. So those are 4 edges that we have talked about. That leaves 2 more surfaces. That's the top surface and the bottom surface. What are the stresses that can act on those 2 surfaces? Let's start with the top surface. Okay, let's go to this notation once again. This is the basic definition. So first of all, once you define the surface, your first subscript is already defined. So what is the value of I on the top?
Is it sigma 3?
Yeah, very good. So I has to be 3, okay? Whether it's the top surface or the bottom surface, it has to be 3, because B3 is the normal to the top surface, minus B3 is the normal to the bottom surface. So both being B3, the first index will always have to be 3, right? What about the second index? Yeah, for normal, what would it be? Exactly. So what shear stresses are possible? Very good. Yeah. So in this particular example that we are taking, we are talking of a pure shear just in the plane. So we will not bring those things into picture. Even if we do, the answer will remain the same anyway. So let's keep things simple. So these are the only stresses which are acting. Okay. But on each phase, as Ivan just pointed out, for the top surface, there can be 3 stresses. Okay. Because once you fix the surface, I gets fixed. But then J can take all 3 values. Remember, I whether it's I or J for that matter, any etc. Any letter you use from the Latin alphabet, which is also in English, you are essentially saying that it will take on this range of 1 to 3, right? So which means that once a particular surface is fixed, only the first index gets fixed. The other index can take 3 values. So on each one of these 6 surfaces of the cuboid, you will have 3 stresses, okay? 3 stress measures or components. Now, so right now, even for this edge, for example, we have indicated only tau 1, 2 because we are talking of a pure shear, okay? There can be one more shear stress on that surface. It's possible. What is that? What would be the notation for that? Other than tau 1, 2 on this surface, what is the other stress that can act? Shear stress. Exactly. So tau 1, 3 can act once again because 1 is parallel to the normal to that surface, and 3 is the direction upwards. So if it were to exist, then it would be in this direction. Throughout, it would be in this particular direction. Okay. Now you can see in terms of the geometry, because our H is very small compared to B and L, because this is either a panel, which is what it is in this case, which we also call as plate sometimes. We could call it, if the bending stiffness is very small, we call it membrane. Or if there is an initial curvature, we could call it shell. In all of those cases, for a statics problem, this check is good enough, that you check that one dimension is small compared to the other two dimensions, then it's fine. When it becomes a dynamics problem, then it's possible that it is undergoing vibrations where some higher modes are dominating, in which case it can go through a shape. For example, this, if I just draw the mid surface of that, then it can go through a shape like this. Okay, it can deform, and this can keep changing over time. A positive might become negative, negative becomes positive, and so on and so forth. It's vibrating essentially, right? So when you have something like this, the H that you're talking about should now not be compared with B and L. It should be compared with a B by 2 and a L by 2, and so on and so forth, as you keep increasing. So in this case it's fine because it's one wavelength, but you could have higher wavelengths of the problem. Let's say you have something like this. So then what you have to compare H with is one wavelength rather than the actual length. Similarly, in this direction also, however it is vibrating, and need not be vibrating in the same way in both these directions, because you typically will have different kinds of loadings, different sizes, and so in this direction I would have to compare with some B by N. In this direction I would have to compare with some L by M in order to make sure that H is small compared to them. So there is a possibility that in statics the same structure can be a panel or a plate, but in a dynamics problem at higher modes of vibration, it may not be anymore a plate. You might have to deal with a 3D model in order to get accurate results. If you go for a plate or a shell model in such a situation where you have higher modes dominating, then you will not be able to get accurate results with a plate model. Okay, in other words, you'll have to continue living with these three indices. You can't reduce it to just two indices. Okay, so let's I'm just taking advantage of this situation to introduce other concepts. That's not the purpose of this particular slide though. Is this aspect clear? Okay, that this check that we do is if it works, then it's fine only for statics. It may or may not be fine for dynamics. Okay, if it's just the first mode that is dominating, then fine, still this will work because your B and L will still be the of the order of magnitude of the wavelength of deformation on those two directions. Okay, now let's come back to the problem at hand. We want to know, will this undergo any compression? What do you say? Let me draw the top view of this instead of a 3D view, instead of the parametric view. Let me just keep things simple. So we have, let's say, this is the x1 v1 direction, x2 v2 direction. Let me get rid of the rest of the board so I have space for other things. So if I look at the same structure from the top, that's how it's loaded. Okay, so this is L, this is B, and we say on the one face you have this shear stress tau 1, 2. And on the top end, it's also tau 1, 2. Okay, so this is a simpler way to look at the same thing from the top, because anyway, eventually we're going to get rid of x3 dimension by lumping all of the material along the thickness onto that mid surface or any reference surface that we choose, right? Now, if this is the situation, we just like to know, in as it looks, yes, we have defined it with pure shear. Is there a possibility of compression in this case if no other extra load is added as it is? Yes? Yeah. Can you explain?
Because it will start changing shape, and then so at the corners where force is concentrated.
Very good. Excellent. Yeah. So if you were to see what, this is of course the undeformed configuration we have drawn. Now we have introduced the stress. Once it is deformed, can you just come and sketch how you think the deformed shape will be? Let's say no boundary conditions are there, it's just free. So it's just, what you said is absolutely right, that the corners will move.
Yeah.
So,
So
which, yeah, you can just say move diagonally. So, okay, very good. Yeah. So, which where is the compression there talking about? Excellent. Yeah. Perfect. Yeah. So Ivan got it right. So what we are talking about is, even though on the original problem definition we saw only shear stresses, the way this is going to deform is such that it's going to extend in a particular direction and it's going to get compressed in a particular direction. So this would be most prominent if you take an angle 45 degrees. But if you take any angle for that matter, you will see a part of the shear and part of this. Okay. But if you say at the 45 degrees, you don't no longer have shear, you have only the tension and the compression. Tension in this diagonal, along this diagonal, and compression along this particular diagonal. Okay. Now that's kind of intuitive to see if you look at the direction in which these stresses are, which are trying, both these arrows are pointing such that this point, this corner, as Ivan pointed out, has to go out. Okay, and if you're fixing this as he did, then obviously that gets out. If it's free, then both these corners will move out by the same amount. You're essentially extending both. And similarly, these two, you can see that the direction of the arrow is such that it is taking the corner into the material, into the structure. So therefore it is moving in. That's essentially what he has drawn over there, right? Now this is also very easy to see in a geometric sense. If you have the shear stress and the normal stress plotted, and this includes both tau 1 2 or as well as tau 2 1, either one of them, and this involves sigma 1 1 or sigma 2 2. Okay, that's not division, it's either or, right? Now when you have something like this plotted as you go for different directions of your 1 and 2, so in other words you introduce a coordinate system xy instead of 1 and 2, then this becomes, instead of 1 1 2 2, it becomes xx and yy. Okay, so this, for example, could be your x direction, this could be your y direction, which are making an angle with respect to your original coordinate system of, let's say, some alpha or theta. Okay, so there's a transformation of stresses taking place within a plane. Okay, so you're rotating the coordinate system by an angle theta, and you, from the x1 x2 coordinate system, you have gone to a new coordinate system xy. Okay, for the special case where theta equal to 0, both these coordinate systems are identical to each other. And once xy becomes theta becomes 90 degrees, then you have an interchange taking place along with appropriate signs as well. And for each one of them, if we do what Ivan did by getting the resultants for each one of them, then, and you for each angle of theta you get points, then we will see that the way this occurs is, in the original configuration you see that there is only shear, there is no normal stress. Okay, so in other words your sigmas are 0, so it has to be on the vertical axis. Okay, because on the vertical axis it is 0. So if you're taking this origin to be 0 0, then you see that the way we define the problem in the x1 x2 system, then for that there is only tau 1 2, there is no, and tau 2 1, there is no sigma 1 1 or sigma 2 2, okay, which is 0. So which means it has to, those 2 points has to be lying on this. And later on we will see that there is a moment equilibrium which makes sure that these two are equal to each other, otherwise this will continue rotating forever. So essentially, if we call that value of tau 1 2 as tau naught, then your tau 2 1 also has to be tau naught in order to make sure that in the limit, because remember stresses are at a point. We might have shown a large panel of length L and breadth B, but eventually what we are looking at is an infinitesimal element around a point, and that's what we are going to essentially take the limit as the size of that particular infinitesimal element in both directions going to 0 to get to a point. And therefore you will see that can happen, moment equilibrium can happen only if both these shear stresses tau 1 2 as well as tau 2 1 are equal to tau naught. And of course that's subject to a particular other additional condition which I will introduce when we bring in the assumptions. Right now let's not bother about that complication. So it's very clear that the problem definition brings in these 2 points, where this is of course tau naught and this is also tau naught in magnitude, right? Now if we start increasing your theta at different thetas, we start plotting, then what we end up is with is a circle, what we call as the Morse circle, right? Have you been exposed to this concept before? Morse circle? No? Okay, so this is a geometric way of determining transformation. We can also do it using equations. So mathematical equations, algebraic equations, which will involve sine theta and cosine theta, their powers. But right now, this is a geometric way of looking at the same thing, right? Now if you look at these 2 points over here, and any point xy you can get to by going angle of 2 theta on this, right? So when you have to go to this 45 degree, you have to go here 90 degrees, okay? Which means that you come up with these 2 points. You start with here for your 1 2 direction, then as you keep increasing your theta, this keeps on increasing, and eventually when theta becomes 45, 2 theta becomes 90 degrees, and therefore you end up with these 2 points, okay? Which is what will be your sigma 1 1 and your sigma 2 2, and you see that one of them is essentially negative, sorry, xx and yy for that particular value of theta, which is 45 degrees, okay? So that's essentially the situation where you have a compression, because this is on the left side of the origin, and therefore this is a negative value, and therefore you have compression, which is what he indicated by this particular figure over here. And if that compression goes beyond a certain value, appropriately you will see that there is a possibility of buckling or instability, elastic instability occurring over there. So that's the reason over there. Now can you think of the third choice that you have here? Is there any modification? Because these are the only 2 things you said that will not have. As I said, the correct answer is all of them, which means that we have already established this, that it is also right candidate. I already have told you this is a right candidate. So can anybody explain why this is a right candidate as well? So in other words, why will a shaft in torsion undergo compression?
It would be a similar reason to this, right?
Absolutely. Why?
It's just since those forces are in the same direction.
You want to sketch here?
So if you have like a circular ring,
Yeah,
forces are similar to this.
right.
So some of this would still.
It is similar, but can you explain a little bit more why it is similar?
Honestly, I don't know.
Okay. Okay. Anybody else?
For your example for torsion, did you mention it's like a bar, you twist it
Uh-huh.
one direction, one
Yeah.
other direction?
Yeah.
So if you use his as like one end,
Yeah.
and the other end would then be like the same thing, but the arrows are pointing the other direction.
exactly.
That's where
Right. So very good point. So both of you, if we put together what you stated, essentially what we are saying is that if we extend this, which is what the shaft is, so this is at one end, whatever you have shown, and Nafeez is saying that at the other end it will be in the opposite direction. That will be the direction of your torque. And so if you take an element over here, essentially it's no longer a plane like what we had in the panel, but now it's a circumferential direction. One is the circumferential direction, the other direction is straight, okay, because along the length of the cylinder. So that particular thing will have stresses like this. Okay, so in other words, we are ending up with a curved panel which is having a very similar stress configuration like this, and the same argument can be used over there, and we eventually arrive at in a direction which is at 45 degrees to this. You will see that the way we have drawn this will be under tension, this will be under compression. So in that direction it is possible that it can buckle. Okay. So the reason why we spent so much time on this, almost 40 minutes, is because this is important from your structural analysis point of view. We remember are in the midst of three types of design basis, which is the strength based, stiffness based, which we covered in yesterday's class. Today we are looking at the situation where we have stability based. Okay, when we want stability based, obviously the stability that we are referring to is elastic stability, or in other words the avoidance of buckling, or at least delaying the buckling. And if that were to occur, we need to know which are the structures which need to be tested for that, and therefore which are the structures in which a stability based design is required, because it's not, those three are not like you choose any one of them and do it, right? All three are usually important for each and everything. You have to check, because if you don't design for strength based, then there is a possibility of material failure. If you don't design for stability, which is what we will do today, then there's a possibility of a geometric failure, because buckling is essentially like a geometric failure. The material is still good, it can take those stresses, values of stresses, its material has not failed, just that the geometry is such that it buckles, right? And on the other hand, if you're looking at the second one that we saw yesterday, which is stiffness based, it just means that again the material has not failed, but the deflections are so large, either the translational deflections or the rotational deflections are so large that it can change totally the aerodynamic shape, and or if it's on the ground, it could touch the ground and the structure could be in risk because of that. Okay, so it's based on that basis that second criteria is also important. So let's move forward. So I don't blame you, because even if you take this sample set that I got for the first time that I had this, I think it was for Phanindra's batch when he took a similar course. So then we saw that quite a few people did leave out these two cases. Okay, so you see that these are shorter columns compared to the others. So you see that people were indeed confused at that stage as well. So this no harm in trying to think aloud and try to find out the right reasoning. Okay, we come to the third category, which is the stability based design. As I already promised, we wanted to include as many different kinds of structures as possible to introduce different concepts. So here we would like to introduce a panel which is having 4 edges, and all 4 are simply supported. Okay, so all 4 edges are simply supported, and then you apply a load P, which is a compressive load. So obviously there is a compressive stress that is generated directly. You don't need to go all around beating around the bush to find out whether it is compressive or not, like we did in the case of the shear stress or the torsion. but right away the very way in which the load is applied is compressive. And once again, the geometry is very similar. It's a cuboidal geometry of LBH, length, breadth and height. Okay, so this is a sheet of thickness H, which is small compared to B and L, and the boundary condition is simply supported. So this notations or symbols we will continue to use throughout for the remaining course. So be familiar whenever I say BC, it refers to boundary condition unless I mention otherwise, and SS refers to simply supported, which means there's a hinge or a pivot on which it is essentially standing, so that it allows rotations freely, but it doesn't allow translations. But if that hinge in turn is put on a roller, let us say, then it will allow translation in those directions in which the roller can roll. Okay, the criterion, of course, because from the name itself we can find out that it's stability based design, so you want to avoid instabilities, right? And that instability in particular we are talking about is the elastic instability called buckling, which can be of multiple types. So but what we are focusing on here is the global buckling, that is the entire structure buckles, but it's also possible that the entire structure is still stable, but locally at certain locations it can buckle. So for example, you brought out the example where the last two things that we had in the previous slide, or last three in fact, all these three, you said that there is still a possibility of elastic instability or buckling. Why? Because you said that one portion will be under tension, the other portion will be under compression. So obviously the portion under tension will not undergo any buckling, but the portion under compression will undergo buckling, which means the structure as a whole cannot buckle in that case, but a part of the structure buckles, which is what we refer to as local buckling, which can, the level of localization can be very different in terms of the length scales. So it can be fairly small portion of the compressive loaded structure which can undergo that instability of buckling, right? The load, as we have indicated in the schematic, is a compressive load, a force P on two of the 6 edges. Then once again, without going into the derivations, you have to take it from me that the critical buckling load, again, just like we talked about natural frequencies, for a continuous system there's not just one single natural frequency but infinite number of them because it's a continuous system. Similarly, your buckling loads also can have multiple values, but the first one or the lowest one is of concern to us, just like the lowest natural frequency in bending, for example, was of our concern in yesterday's class. So that critical load, without giving the full expression to it, we are just taking what are all the parameters that it is proportional to or inversely proportional to or proportional to at a different path, and we are just taking those which are of significance to our design, either from the material point of view like the Young's modulus, or from the geometry point of view like your H and B, right? So it's proportional to EH cube by B. So it's very interesting that as far as the third direction is concerned, the thickness direction along which we define the coordinate measure x3 or the unit vector b3 is the one which is dominating the behavior of this. So if you want to avoid buckling, even a small increase in the thickness may be able to do the trick for you, okay? But increasing E or decreasing B will not do as much of the trick. And why this is so? Of course, again, this is also taken from Olivier Bauchot and Craig's textbook. So in this portion, they only give this, but they refer it to another portion of their own textbook to show you, if those of you are interested, which is beyond the scope of the or syllabus of this course, to see how they arrive at this particular expression, okay? So we will take it for granted that's true and we will continue, okay? Once again, it's a lightweighted structure, there being an aerospace structure. So once again, apart from the main criteria, we are always interested in the mass and somehow bringing that mass and factoring it into the whole problem. Therefore, once again, it's a cuboid. BHL is the volume multiplied by the mass density, rho is the mass. So we take that, and now we can eliminate one of the things we have a command over as structural analysts or designers, that is the thickness or height H of this panel. And then because we can play around with that independently, we want to eliminate that, which means that I can substitute for H as m by rho BL into this, and then of course cube it, and then I can do a little bit of shifting around to eventually show that it depends on two factors multiplying each other, and one of those factors is involving the mass and the geometry, and as we said, L is associated with, let's say, and here remember, we are not talking of the entire wing, because if we had talked of the entire wing, we would have shown one end is clamped, that is fixed, all the other three edges are free, so that's like a cantilever kind of condition. But here remember, we are showing simply supported at all four edges. So in other words, we are saying that on the wing, we know that in cruise or most phases of flight, the lift distribution is going to make the wing bend upwards, which means the top surface is under compression. So the top surface is not a single panel usually, unless it's made out of integrally manufactured co-cured composite. It's usually, for large aircraft, it's multiple panels which are stitched together through rivets. Okay, so if you take one such panel, then the rivets can be thought of like hinges, and therefore this is a crude assumption, but essentially the first step that you can take towards understanding it qualitatively. So that's why we can think of all those four riveted edges of a single panel on top of the wing to be simply supported or hinged or pivoted, and therefore once you have something like that, your B and L, you have a little more play over compared to what you had when the entire half wing was considered as a beam. Then it became the span, and the aerodynamicist had the full say over that. But now that entire span, you're breaking it up into multiple panels. So how many panels you break it up into, each panel's size will vary, right? So you have a little more control over that. So just like H is a design parameter, to some extent B and L can also become design parameters, because B is along the chord and L is along the span, but it's not the entire chord, it's not the entire span. It's smaller than that. It depends on how many panels you have along the span, how many panels you have along the chord, based on that. And they may not be equal in length, equal in dimensions. You could have different. So each panel has to be analyzed separately for that. This M is the mass of that particular panel alone, not the entire wing, right? So that's of less interest for us right now, because we are focused on materials. This is of interest from an overall perspective, a holistic perspective, where from the 20 to 25% of the overall aircraft weight, what has been allocated for structures. Out of that, different parts, the wing, tail, fuselage, etc. And within the wing, some allocation of mass is made for a particular panel, and that is that M that we are talking about. Whereas B and L are the size of that panel along the breadth and the length. And the thickness we have eliminated, because that's a design parameter, how thick the panel we want. Now what is of more importance to us is the second factor here, to multiplying the first factor to get to your critical buckling load. So if you want the critical buckling load to be large, you want through the material, by changing the material, you want a material which has a larger E by rho cube. So that's essentially what you want to move towards, which means that unlike in this stiffness based design where you had a square root of E by rho, if it was a dynamic criteria, if it was a static criteria, it would just be E by rho. Here we have a E by rho cube. So in other words, the dependence on rho is much larger, and it is primarily coming from this cubic dependence over here, because it was very sensitive. The critical buckling load is very sensitive to the thickness, therefore it is very sensitive to the density of the material as well, and which is what makes lighter materials much more significant in a stability based design. And there's a large portion, as we already saw from the previous slide, of the structures, even though they may not be directly subjected to compressive load, through bending or through torsion or through shear, they are subjected to compression in other directions than the actual load. And therefore it becomes imperative for us to bring in that test, and which means that this particular factor of E by rho cube becomes so critical in the choice of the material. So for a given mass and geometry, which means that M is fixed, your B and L are fixed, the panel size is fixed, and we've already eliminated H anyway. It's not occurring in this proportionality. And for that, we see that the factor of importance, which is called as the performance index for stability based design. Just like sigma u by rho was the performance index for a strength based design. That's what we did in the first half of yesterday's class. Then we saw square root of E by rho is the material performance index for a stiffness based design. That's the second thing that we learned yesterday. The third thing, which is a part of that whole game, is the stability based designs material performance index, which is now shown to be E by rho cube. Is this clear? Any questions on this? Okay, let's move on. So now we have all three in place. Now we have a better rubric to compare the materials that we have on hand, right? So we had started off with just three metals, all metallic alloys, iron based, which is steel, titanium based, or aluminum based, right? So we will continue to take them, because earlier we were talking about only in terms of absolute values of sigma u, we were comparing absolute values of E, we were comparing absolute values of rho, and we arrived at different conclusions based on that. Now that we have performance indices which combine rho with these material properties like E or sigma u, now we can do a much better job. Now remember that I had shown a very large value for the steel's tensile strength, all the way up to 4.1 or 4.2 gigabyte, if I remember right. Okay, but if you look at the auto industry, and this is cutting edge, one of the latest information from the world auto steel, you see that you can go only up to about 2 gigabytes, 2 gigapascals, that we have too much of IT here. So seeing all these laptops, and that's what is coming to my mind. So 2 gigapascals is what is the maximum, and that is the cutting edge third generation high strength steel that you have, advanced high strength steel. But I had put something as high as 4.1 to give you the cutting edge over there. Just about in 2022, a Chinese group came up with a new steel. Again, it's not in the form of panels that we want over here, but they could draw wire out of the steel. Typically, most of these steels are made with, of course, after alloying, certain level of heat treatment that goes through that, right? Whereas this particular steel that I refer to as 4.2 gigapascals is something that was cold drawn. So in other words, there's no heat treatment done to that. It's just done, everything is done, the entire manufacturing process is done at a lower temperature, because of which they were able to draw wires which had a tensile strength almost double of this. Okay, still it's not of much practical application as yet, because making it in such large quantities and making it other form factors than wires alone or cables alone will be difficult, but things are moving in that direction. So that's why it's very important for us to understand, even within the auto industry itself, such a wide range, almost to a factor of 10, starting from 200 megapascals all the way to 2000 megapascals. It's a factor of 10 that we are talking about, the stretch of the steels that are used within the automobile industry. And so it's very important when we refer to any one of these alloys to be more specific and talk about a specific alloy rather than in a broad sense, because otherwise you'll have a large range. So I would like to once again warn you that the values that we dealt with in yesterday's class were all ballpark values, just typical values. It need not be the actual value, because it can have a fairly large range. One more thing that I didn't talk about as an important property here is on the y-axis, the vertical axis over here, which is the elongation percentage, and that becomes critical for certain applications. For example, if you want this in impact kind of applications, which is very critical in the aerospace application of steel, primarily for the undercarriage, which is the landing gear, where it is undergoing compression directly when it is landing. If it's a hard landing, then the compressive stress can be fairly large. Of course, it has hydraulic systems, pneumatic systems, all those things which take a lot of the compression, but the steel is also required to take a lot of the And of course you have the tires, and the tire design again is a composite design, which is a very, very specialized design for aircraft tires in particular, right? Leaving all that, even the steel that is used there needs to have a very advanced or high performance in compression, right? So when you're talking about that, especially for hard landings, and this is actually a fallout from automobile industry once again. If you look at the cars and the initial history of the automobiles, let's say about 150 years back, the manufacturers like Ford, etc., GM for that matter, took pride in the fact that their structures were rigid. So they had really rigid structures, and they used to show that it's very, very difficult for them to fail. But what happened in crashes is that that structure remained rigid. It was not destroyed, but that was not actually an advantage, because all of that crash energy was directly transferred to the cabin and the people sitting in the cabin, the driver and the passengers, and therefore more of those accidents were fatal for the people. The car survived. So then people realized the priority is people more over the vehicle, and therefore we said, let's design it in such a way that the front portion of the car, when it's a frontal crash, let it undergo such a large deformation and even damage, such that it absorbs a lot of the energy already, and only a smaller fraction of the energy is transmitted to the cabin. So you still have, of course, people dying and various other issues, but the numbers have come down in terms of the passenger kilometers that we have. If you compare to that, it has come down drastically because of this change in the paradigm shift in the very design, where we allowed for the vehicle to be crumpling and therefore absorbing a lot of energy of the impact into this. And that's a science by itself. Low impact, low velocity impact, high velocity impact, or medium velocity impact, the behaviors are very, very different, because the strain rate behavior comes into picture. Here we are talking of just a static deformation, how long it can get extended before it eventually breaks. These are ductile materials, so they enter beyond the proportionality limit and the yield. It becomes inelastic, and in the inelastic regime, much larger elongation is possible, and you see that it can go all the way up to almost 80%. That's almost doubling the size of that. So it's of course, those are some very specific steels, like the austenitic stainless annealed steel, particular heat treatments of like annealing that is involved over there. But otherwise, you should know that, because we are getting into composites, we should know not only the advantages of composites, but also some of the disadvantages, because many of these polymer matrix composites are brittle rather than ductile, and they might fail at a much lower elongation percentage, though we might be able to stretch this a little further onto the right. Okay, so it's all a question of give and take, which is more important for a particular design, for a particular component within that overall vehicle, and then we have to make the appropriate choices. So many of the abbreviations, etc., that are mentioned here are not of much significance for us, but essentially it talks about the composition of those alloys and the kind of heat treatments, etc., that they are undergoing. And some of them involve abbreviations standing for what is the purpose of that, like the advanced high strength steel, etc. Okay, so now we are at a stage where we can combine all of that we did in the previous class and the first half of today's class, where we can summarize that the design based on three different criteria. One is, we don't want the material to fail, we don't want the material of the structure to deflect too much, and then we want to ensure that the material of the structure avoids or at least delays buckling. Okay, so these are the three criteria that we have. And this, of course, was also because of the power 0.5 ensured that the natural frequencies were also large enough so that resonance can be avoided, either air or ground resonance, which could be deleterious as well. So that's the thing that we talked about, but only the first three rows, apart from the title row, is what we already introduced in the previous class in terms of these values for sigma, u, rho, and E. And once we substitute that and calculate the ranges, actually all of them should have a range, but usually E and rho do not change across alloys so much as sigma u does based on the heat treatments, etc. So that's why I've given ranges for this, whereas I've avoided giving ranges for this because these are reasonably good mean values to work with, okay, average values to work with. But what we have added to that information today is the last 5 rows over here, which are all composites, okay, and the first 3 of those are polymer matrix composites. The last one is also a polymer matrix composite. One which stands out here is a metal matrix composite, because I want you to be aware of the fact that it's not always that polymer matrix composites are used, though that is the dominant composite that is used in a lot of aerospace applications. Slowly we are moving based on the high temperature requirements to metal matrix composites or ceramic matrix composites, even carbon-carbon composites, etc. So we need to be aware of their properties. So when we talk about the advantages and disadvantages of composites over metals, we will mostly be referring to the polymer matrix composite, but some of those may not be valid if the other types of composite like MMCs and CMCs or CCs are taken into account, which are the abbreviations for metal matrix composite, ceramic matrix composite, and carbon-carbon composite respectively. Now coming to the values, once again here I have given to start with a single value, but once again these can also have a wide range of values depending upon the specific fiber, depending upon the nature of that matrix, because there are so many different types of epoxies, so many different types of aluminum alloys, etc. Boron itself is not actually entirely a boron fiber, but a carbon fiber which is coated with boron, and therefore it has different properties from carbon. And you see carbon appearing twice over here other than boron as carbon epoxy and graphite epoxy, because graphite is also a particular crystalline version of carbon, just that within the composites industry or the fiber manufacturing industry, you typically refer to a slightly lower percentage of carbon in terms of the purity. You call it a carbon epoxy, whereas if the it's much closer to 100% carbon within the fiber, then you refer to it as graphite epoxy. And so that's once again the case. So you see a slightly higher value over there, but it could be a range because you want to increase sometimes the purpose is to increase the E, the Young's modulus, more than along the fiber direction, of course, because now we have to start talking about directions now that we are dealing with materials that are not isotropic, what we call as anisotropic, right? So now let's first focus on the first 3 rows, because those are the materials we introduced yesterday. And there once again you see if we factor in rho, because yesterday's comparisons were all only with sigma u, only with E, and then only with rho. With sigma u and E we came to a conclusion that steel is the best. With rho alone we came to the conclusion that aluminium is the best. Now all these factors that you have in the column heads are combining either sigma u or E with rho, so that you have a weighted way of comparing, and these are derived based on actual structures, their behavior, and therefore we came up with this. And the units are also very interesting, because your sigma u and E are having the unit of Newton per meter squared, whereas rho is having kilogram per meter cube, and the Newton itself can be broken up because you use Newton's second law, force is equal to mass into acceleration. Mass has the unit kilograms, acceleration has the unit meter per second squared. So Newton is nothing but kilogram meter per second squared. So once you combine that with rho, you see that the kilogram gets cancelled in the first 2. The last one, because it's involving different powers of E and rho in the numerator and denominator, the kilogram remains, okay? Whereas the SI unit for this is meter squared per second squared, because it's a large number. We are factoring out 1000 as well, and here again we're factoring out 1000. This is having the same units as speed, and this has the very strange unit of meter per 8 per kilogram second squared. So what is important is not these absolute values again, but across the rows, a comparison which is more, which is less, and which is much more compared to something else, so that design decisions can be made in a much more informed way than comparing just the absolute values of sigma u, absolute values of E, and the absolute values of rho. So here we have a actual performance index that we are comparing, and when we do that, very strangely we see once again steel is the winner. We thought that if we bring in the rho factor in which the steel failed miserably, maybe the aluminum alloy will win or titanium alloy will win, but no, you still see that the steel is winning that race for the ultimate tensile strength, even when the weight is brought into picture through the density. Okay, but the transformation takes place when the factor that is involved, the performance index, is much more strongly dependent on the rho, which is for the stability based design, where we have a rho cube in the denominator, and there you see there's a huge difference. So this is almost what 7.4 factor that aluminum is better than steel. Okay, and stability based design is important, as we showed, not only for structural components actually subjected to compression, but even those subjected to bending and torsion and shear, because in other directions you could have compression and therefore instabilities occurring. So this test is what determines aluminum alloys dominated the aerospace structure or materials industry for such a long period of time, is because of this 74 times that you have advantage over steel. But if you are sure that a particular structural component is not going to have any compression at all, then the difference comes over a stiffness based design. These are equally good choices, aluminum alloy or this, and the titanium alloy is only inferior by a very small amount. Once again, as I said, there could be a slight range, but because E is not changing too much across the titanium alloys, so you will not have too much of difference. That's why, as I said, we don't have ranges over there. Whereas here you can have a fairly large range. And again, it also depends on which particular steel we are talking about. If we compare the largest value over here, yes, then there is a difference. But if we are looking at other grades of steel, there are grades of titanium which are better than that. Okay, and similarly, an aluminum alloy which can be comparable with the steel alloy over there. Okay, so we need to be more specific rather than bunching them all together as steel. So you should have multiple rows for the different kinds of steel, etc. Okay, and even here, even though I've given single values, the volume fractions can be different, and the epoxies of different grades and the fibers of different grades can make these also fairly large ranges. These are some of the typical values used of composites used in the aerospace industry that we have taken. It's more has to be taken from a point of view of an order of magnitude rather than exact values. But you can see already we are moving into the thousands instead of the hundreds, and that's where the advantage you already see even in specific strength, much above even steel. And then once it comes to the others, it becomes even more important, especially in this. You see a factor of 89. So already compared to these two, you had such a huge advantage. Now you have an even bigger advantage that you are looking at with graphite epoxy. So once again, as I said, graphite and carbon differ in terms of the percentage of purity of the carbon over there. Are there any questions related to this slide? No? Okay, let's move on. Okay, so now that we have seen from the previous slide the huge advantage that composites bring in terms of all these three material parameters, irrespective of whether we have a strength-based design, stiffness-based design, or a stability-based design, it becomes obviously imperative to get into composites, even in a basic course like this. And also, that's also what is the trend, as we already discussed, in the aerospace industry, whether it's aircraft, helicopters, rockets, missiles, satellites, they're all using composites extensively. So if you're not aware of how what these are and how they work and how we can analyze structures made out of them, then our structural analysis course will be a waste. So let's go ahead and we will ask 4 questions and try to answer that. Most of our course will be based on the last question of how do we analyze composites, because that's structural analysis. As any aerospace structure made out of composite, how we can analyze, and because we are dealing only with healthy structures which are not yet undergone damage and which are still working, therefore the model remains very similar for metals as well, metallic alloys. So just that it's much simpler, so a special case of that we will reduce it for that. But before we get to the how, which will dominate our course, we want to briefly spend some time, maybe a couple of classes this week, to understand the why, what and where as well. So in other words, we want to say why are composites used, and if the previous slide was not convincing enough, because the previous slide already showed from the 3 performance index point of view the huge advantage that composites have over the alloys that have been typically used in the aerospace industry, in particular the aluminum alloys and even steel for that matter. Okay, then we will, but we want to give even more reasons for that. There are many other reasons which we will not go through in the quantitative sense like we did in the previous 3 design criteria, but we will go through it in a more qualitative way. Then we will more specifically define what are composites, because most people think of it as mixtures, whereas alloys are also mixtures. It's not that composites alone are mixtures. Okay, alloys contain so many different metals. So what is it that makes composites distinct? That's what we will look at second. And finally, we will look at some sample examples within aerospace where they are used. And this of course goes with your assignment as well, where you already showed for the different Indian aircraft and launch vehicles where these are being used. So you already have an idea from the work that you have done. We will look at a few more specific examples of that. Okay, so let's start with the first question, why? Okay, so which means that if we want to use composites, we have to give some reasons for that. The previous slide was a great, excellent reason, but are there additional reasons? Okay, so we have to look at the merits of composites with respect to conventional materials, and we will do it in a very interesting way. We will start with the demerits or the disadvantages of using composites first, to be aware that when we are introducing composites, everything is not hunky-dory. Okay, so which is the reason why metals continue to be used at least in smaller portions, smaller percentages in many of the even the current aircraft and flying vehicles. So we will look at some of the disadvantages first. Then we will see, in spite of those disadvantages, can we still use composites because of the huge advantages that they have, and how do we overcome some of those disadvantages, because we should be aware what is the issue they bring in and how we can resolve those issues. So, and when we say conventional materials, we're referring mostly to aluminum alloys, but also titanium and steel. Next, in answering the question what, as I already said, we will not only talk about the definition of composites, but we will go into examples of their constituent fibers and matrices, and when you use which fiber, when you use which matrix, and what is the functionality of the fiber, what is the functionality of the matrix, what happens if one of them is not there. All these kinds of questions, mostly qualitatively, we will try to deal with. The third question is the typical applications. What are the kind of aerospace components which are made out of it, and why? Finally, we will look into, for most of this course, what is called as the mechanics of composites. And mechanics of composites involves 2 portions. One is at the lower material level, typically of geometries of the order of the fiber diameter, which is typically of the order of a few microns, let's say around 10 microns. And then that's what is called as micromechanics. And then we will go to macromechanics at the structural level. And if we want to do that, we have to bring in an intermediate level as well, what we call as mesomechanics, to bridge the theories at the fiber matrix level to the composite structure level. And so we will do micromechanics, mesomechanics and macromechanics, and we will keep the details which is within the understanding of typical undergraduate courses of undergraduate students. So that's essentially what we'll do. And while the focus will be on the analysis, we will also keep talking about the relevance of it for the design as well, because most engineers eventually work in design kind of situations, unless they're doing, let's say, an accident investigation, etc. Even in which case we look at from the accident investigation takeaways. One of the important takeaways is to how to modify the design so that such accidents can be avoided in the future. Okay. Now, this is the way in which, though we are specifically dealing with composites, it's very important pedagogic concept that you should know, that for learning anything, not only in this course but any subject for that matter, by asking questions, thinking aloud to make sure that you understand why you're doing certain things, what exactly you're doing, where it is going to be eventually applied, whatever you're doing, and how you're going to approach the problem, because there are many different methodologies that you can use to do that. And this is where the Indian system of pedagogy has been really impressive, not only from an engineering perspective but also other aspects like philosophy, etc., where most of our learning has been through asking questions. So a student goes to the teacher, asks questions, and based on the answers that are provided, the student continues to think further and ask questions out of himself, and the answers that he gets, out of that something innovative comes out. So that's very important for you to see if you can bring in this kind of methodology to study for many of the other subjects that you're studying as well, because at least in my experience it has helped, and many of our students and alumni, and they keep vouching for this kind of an approach being of great relevance to them even in their careers, leave alone while they were students. Okay, now before we leave this slide, it's a particular reason why we have this particular picture over here. We had talked about some transformations over here as far as the shear is concerned, and we saw it's not just the magnitude of the stresses, but the quality itself or the type of stress itself changed from shear to tension and compression. That is from a shear stress to a normal stress, two kinds of normal stresses. And those kinds of things are going to become very critical, especially in composites, because in a given layer you typically have the fibers in one particular direction if it's a unidirectional ply that you're dealing with, or at the most you typically deal with woven fabrics, in which case you can have at 0 and 90, which are weaves, just like our the fabrics that we wear as clothing, something like that. So typically you will have weaves in that direction. So but more often than not, you will be using in each layer a single direction fiber, which is called as a unidirectional ply, and you will be stacking over that plies which are having fibers in different directions, so that it can be capable of taking loads in multiple directions. The reason is, we will see in terms of actual numbers a little when we go a little forward, but right now it suffices to see that the way these fibers are stacked up over here, if I pull along this x1 direction here, it's going to be much tougher to cause any deformation, because the fibers are very stiff, and it will also fail at a very large load when I start increasing the load in the x1 direction. But if I pull it in the x2 direction, I apply the force parallel to x2 that you see over here, what I'm doing is I'm trying to pull the fibers apart from each other, and the thing that is resisting them is the matrix in between two fibers, and the matrix is very weak compared to the fibers, weak in a sense of the strengths being small, but also in terms of the flexibility, and therefore the Young's modulus is also very small, and you would see much larger deformations, and beyond a certain point it will much more easily fail in this direction compared to this direction. So this is something that we have to be aware of. As I said, though we are mostly going to discuss the advantages of composites, we should be aware of the limitations, and this is one of the limitations you have, but there is a way of overcoming that. What will I do? Apart from this layer, I will take another layer in which I have fibers only in the x2 direction. So, and these will be bonded to each other. So now the overall structure, let's say, has two layers, Now whether I apply in the x1 direction or x2 direction, I have at least one layer which is going to resist that, which is going to reduce the deformations or strains, and also delay the failure, and therefore there's a way of getting out. So it's very important for us to understand not only what is the issue, but how you can overcome that issue, what is the resolution for that issue, and there could be multiple ways of resolving that issue. So this is one way of resolving a particular issue that I wanted to bring to your notice. Okay, so as I said, we will start with the disadvantages, which is why the heading of this slide is why use composites in spite of. So what are the issues that are associated there? And what we were discussing in the previous slide on the schematic of a ply is more clearly evident if you look at this particular graph, which is plotted for three composites. Two of them are polymer matrix composites, extensively used in the aerospace industry. For more critical locations where the stresses are large, you use carbon epoxy. Where the stresses are not that large or the deflections need to be curtailed, we use typically glass epoxy. And then where the temperatures go a little higher, let's say in the fan stage or the compressor stage of the engine, we can go to a metal matrix composite. Behind that, in the combustion chamber and the rest of the engine that you have, you will see that the turbine and the nozzle, you will see that the temperatures are even higher. Even aluminum will not do, so you'll have to go for other materials. So irrespective of which of these three composites we are considering, there's a trend that you observe in this. When you change that angle theta degree, which is essentially that same thing that we saw over here, this theta that we are talking about, the direction in which you're putting the fiber relative to the structural axis. The structural axis could be, for example, along the span and along the chord of the wing. Okay, so relative to the chord of the wing, what is the direction in which you're putting fibers in a particular layer will determine how it responds to the different kinds of forces and moments coming on it, right? So if you look at this particular thing, you see that for theta equal to 0 degrees, which means that once again, if you look at it, theta equal to 0 degrees means the fibers are parallel to the x-axis, and there if I apply a force which is essentially like the drag, for example, I'm applying in a particular direction, then you see it behaves very reasonably very good. But once you go to theta equal to 90 degree, the value of the Young's modulus drops so drastically. And though this is Young's modulus that we are plotting over here, a similar kind of a trend will be there for the strengths as well. So the strength will also drop. It will be highest for 0 degree. For the same composite, when you go to 90 degrees, it will be the least. And in between, it will be somewhere between those two extrema. And you see that the drop is quite drastic upfront. So in other words, even a small change from 0 degrees, you're having a huge drop. Whereas from 45 degree onwards, you see not too much of a change. Yes, there is a reduction, but the amount of reduction is very, very small. Okay, so when you have to have 0 degree, the tolerance that is required in terms of the actual placement of the fibers, whether it's hand layup or any other more complex automated layups like using laser guided systems, etc., that we have. So you have to be as precise as you can, and improving the precision of that layup is one of the important aspects of composites research as well, and that's where you can maximize the benefit, because you see it drops from 14 to 12 just going from 0 to 10 degrees. So if you are having a very small change which is unintentional, just because you are not very careful in your manufacturing process or some issue with the machine that is manufacturing it, etc., then you can have a fairly large drop, and what you have designed it for might be 14, but the actual thing on offer by your material will be only 12, and therefore you can see a huge difference over there. And here we are talking of not absolute values, we are talking of a factor over here, a non-dimensional quantity. We are comparing with what it is for the 90 degree direction. So in terms of that, it is 14 times, so that large. Okay, so that's the measure of an anisotropy as well. There are many different measures of anisotropy. Remember, isotropy, which is the property of metals, is that the properties are the same in all directions at a given point. But in composites, properties are different in different directions. One measure of that is how large is the 0 degree modulus compared to the 90 degree modulus, and that for some of the composites like carbon epoxy can be as large as 14, whereas for some other composites like what you see here, boron aluminum, it's not much, it's very close to 2, it just doubles, right? Why? Because boron and aluminum have comparable Young's moduli, whereas carbon and epoxy have very drastically different Young's moduli. So when you are having such a difference, this is what eventually happens. So let's look at a few other disadvantages as well. One is the very fact that it is anisotropic. Also it is heterogeneous, that is, somewhere it is a fiber, somewhere if you go to a different point very close to each, that is just a few microns away, it's only matrix, right, in the actual structure. So there is a fairly complex way in which you have to characterize these materials. Whether you do an experimental test to characterize that or a theoretical characterization you do, in both of them the complexity is much larger than when you are characterizing metals or any isotropic materials. Okay, so both in theory and experiment you have a complex material characterization. As I said, I'm not only going to be talking about the problems, but how we can what is the repercussion of that and how we can resolve that, right? What is the repercussion of the fact that the characterization of these materials is complex? Complexity always means that more people have to be involved, or more number of hours for the same people need to be involved. So in other words, a lot of time of the industry goes into characterizing these materials, which was much lesser for the metals that they were using earlier, which means the time taken for design is going to be much more. There's this upward arrow that I already introduced to you in the previous class that just refers to a very large value, and the cost in terms of dollars also is very large. Many a times in the aerospace industry at least, this is much more important for us than this, because if you lose some time then or delay it, some competitor could come up with a similar kind of a design faster to the market, and they might capture the market because the number of players involved in the market is very few. The earlier they are able to access your vehicle, they typically go for that, unless there are many other huge differences and they're willing to wait. So many a times, even if it means a little higher cost, you might still be okay with it, but if it's a huge delay, then you really want to avoid that. Okay, so this is a factor that you need to be aware of. So let me say how you actually overcome that. So anisotropy is typically overcome by taking into account the angular dependence of this material, and also going in for the homogenization of the material, whereby the heterogeneity can also be taken care of, so that you're not dealing with point to point variations from fiber to matrix, because that really doesn't matter unless you're doing a damage mechanics and trying to understand it in a phenomenological sense, whether it's a fiber breakage or a matrix cracking or a fiber matrix debonding or something else which is kind of combination of these, or delaminations, etc. Only then you need to understand where the fiber is, where the matrix is. Otherwise you can have equivalent homogenized properties whereby we are introducing certain imaginary materials which behave exactly like that layer, but point to point it may not behave, but overall deflections, overall strains, overall failure values, etc. will still be the same. So you can deal with that kind of a model in between. So in other words, there is an issue that can have terrible repercussions from a business point of view, but there is a way to overcome that, and that has been done for quite a long period of time now, and it's almost used on a routine basis. So be aware of the issue, but also of the way in which we have resolved it. The second issue that we'll be talking about here is the susceptibility of composites to impact, okay, which is much more than in the case of metallic structures. Why? Because we saw, for example, in that plot we had for the auto steels, the percentage elongation went all the way up to 80-90%. So it's essentially a material which is ductile, and therefore a lot of the energy absorption can happen in the deflection even before the actual permanent damages can occur. So in the elastic limit itself, it absorbs a lot of energy, and in the plastic limit with some amount of permanent deformation, it can absorb energy, and beyond that in the failure process also it absorbs a lot of energy. So whereas most polymer matrix composites are susceptible to impact, so what you will do is you will use fibers which can absorb a lot more energy. For example, you still have a polymer matrix composite, but if instead of carbon fibers or glass fibers, which are brittle too, if you can use Kevlar fibers, for example, they are essentially polymeric fibers, and since they are not thermosets, you essentially have a much larger deformation that they will allow, and therefore they can store a lot of impact energy, and you do something like that. Or you might go for metal matrix composite, etc., in which case you bring in the ductility advantage of the matrix into the picture so that you can overcome these issues. So that's the second botheration of composites. The third botheration is kind of severe in certain applications like marine applications, etc., which we discussed earlier as well. Let's say naval aircraft which are on aircraft carriers, which are taking off and landing on aircraft carriers, exposed to a humid atmosphere. Also the water content has some salt content in it as well, which makes the thing much more corrosive in nature. So that can degrade the properties, some swelling of the matrix can occur. Overall the performance of the matrix and therefore of the composite comes down. So even in metal matrix composites, like certain times there can be corrosion issues because of that moisture. So that moisture pickup is something that you need to be aware of. So how do you go about dealing with that? So it has to be through some kinds of coatings that you have, or some kind of appropriate addendum that you have in the composite other than the fiber and the matrix, which can kind of compensate for this, and therefore even though that issue is there, it is not as large as it would be without those additives. Next important thing, especially when you're using thermosets like epoxies, which has been the trend for most composites in the aerospace industry, these are not recyclable, and that's been a huge issue for the environment, and therefore people are moving in the aerospace industry slowly to thermoplastic matrices like polyether ether ketone. Even though their manufacturing is a little more complex, at least those can be reused, like some of these other applications of plastics in other industries. We have learned from that, but of course we need much more high performing matrices apart from fibers, and therefore also the compatibility between the fiber and the matrix is important. Taking all that into account, still we are moving towards the possibility of recycling. And when we say recycling, both the fiber and the matrix have to be recyclable. There's been a lot of effort over a period of time in bringing in recyclable fibers, like plant-based fibers like jute, etc. People have been using for a long period of time, especially in the automobile industry, for secondary structures like doors, etc., even in high-end cars. Whereas that's not good enough. You have the main culprit there is the matrix. So if you have not changed the matrix, you're only changing the fiber from glass or carbon to natural fiber. Yes, you help in a certain way. It's cute, like gardening instead of foresting, right? So whereas the real thing is, if you want to make an impact, you work on the forest rather than just your home gardens, right? So that's the same thing over here. Instead of already a lot of work being done on fibers, not to belittle that, but the more important work that needs to be done in terms of recyclable matrices for composites. The next thing that is a disadvantage when you are using composites is, while they are really good at in the fiber directions, we saw over here, once it goes to the other direction perpendicular to the fiber, which we call as the transverse direction, the transverse properties become very low, and also the shear properties are fairly low. So whether it's transverse shear or the in-plane shear, you will have much lower strengths and stiffnesses, not as huge advantage as you're going from metals to composites in terms of the properties along the fiber direction. Yes, huge improvements in the strength and stiffness, but anything perpendicular to that or in shear, it's not that huge advantage. Sometimes it might even be a reduction. So how do you go about doing handling that? As we said earlier, for one of the other things, you bring in layers which are at different angles, so that what is the transverse direction for one layer will become actually a longitudinal direction for the other layer. If it's, let's say, 090, which is a cross ply, then you can take advantage of both of them operating simultaneously. So that's true whether it's strength or stiffness. So most of the things that we have listed on this slide can be overcome by proper laminate design, even moisture pickup for that matter, because moisture pickup might be in a certain way for a particular layer. You can design another layer to compensate for that and make sure that the moisture pickups are kind of compensated as well. So there you go in for what are known as hybrid composites, where you have different fibers and or matrices in different layers, but again the compatibility is important between the matrices and two layers, otherwise delamination could be a problem. So a lot of thought has been given both by the academia, researchers in the academia, as well as those in the industry, in order to overcome some of these things, both experimentally as well as theoretically, getting inferences from the theory in order to understand the computational aspect and therefore the eventual change in design that is possible. Then another thing which is there in the metals as well is uncertainty in properties. So if I buy a lot of by lot I don't mean large quantity, but a lot is essentially a particular fixed quantity of things that I order from a manufacturer. Different portions of that lot itself can have slightly different properties even in metals, but that variation is not as much for metals as it is for composites, because these come in the form of we will see shortly things like sheet metal, compound, etc. Also prepregs, which is the most common form of the raw material for composite usage. Then you will see that within the prepreg the properties can vary at different locations along the prepreg when you make specimen, as Fanindra is discovering for some of his experiments, large variations in the properties, in which case you cannot use the deterministic models that we are so familiar with. We have to go to what are known as non-deterministic models. In other words, instead of giving these values, the properties that we talked about, a single value or even a range, we have to give the probability density distribution function for these, how these properties vary, what is the percentage of certainty with which we can say the properties within a particular range, etc. And therefore your end results in terms of all your sizing, shaping, etc. will also come within a range, and therefore you have to make qualitative decisions and then eventually quantitative decisions. All of that are ways of handling that. So again, that's a huge area of research, non-deterministic analysis, how to do uncertainty quantification, not only at the material level but at the component level. Looking at the entire wing for that matter, so many different materials are used. Each of them have different uncertainty values for different properties, shear, the stiffnesses, the strengths, etc. All these things have to be accounted for, and eventually your final takeaway from that has to be, arrive. And so these are typically big data problems, because a lot of complexity is involved in the materials, and also the probability density distribution functions bring in their own complication as well. For a long period of time, this was done using the power of the computation through things like Monte Carlo methods, where you try to have a random distribution within the range that you are interested in, and you try to fire it up and try to get the properties. But over time, we've seen that, especially when you're dealing with a large component like entire aircraft wing, that is not a practical approach to take. Much more intelligent ways of handling these kinds of problems have to be done, and that's the domain of some parts of aerospace structural research today. So any questions on this? Yeah. Okay, so now we have looked at most of the disadvantages there, but now we come back because we have said that those disadvantages can be handled in some very easily because of the long period of time that we have worked with these materials, decades in fact, and therefore we know how to handle these things. Yes, it's an issue, but that's a resolvable issue. So now we get back to the advantages of composites. It's for no reason that they find so much of application in the aerospace industry. And the first thing that we have already seen in one of the slides today, where we compared sigma u by rho, E by rho per half, and E by rho cube for the metals versus the composites, we saw that orders of magnitude difference exist over there, which means outstanding specific mechanical properties that alone by itself is a huge reason for us to move for composites, was the reason, and that's why it has been done over the last few decades. So these are the three properties that we're talking about. Then coming to the other advantage is that unlike in metals where you choose a material and then the rest of the design is all about geometry, shaping and sizing, whereas in a composite you choose a fiber, you choose a matrix, you have already chosen the material, but still you can play around with the volume fractions, you can play around with the layups, not only in terms of which angle plies to take, but in which order to stack them up. For example, if you have 0, 30, 60, then it can be either 0 over 30 over 60, or it can be sandwiching the 60 in between and having the 0 and 30 on the top and the bottom. Properties are going to be very, very different from each other. So there's a lot of tailorability. In other words, a lot more flexibility in the sense that you're not only designing with the shape and the size, but the material itself. Only one aspect of the material, namely the choice of the fiber and the matrix, has been already done, but you can still play around with so many of the smaller scale geometry factors like volume fraction, etc. They're also essentially geometry, and also these angles, etc. They're all geometry, but geometry at a much lower length scale than the structural geometry, and therefore you have a lot more flexibility, and therefore you can achieve things which you cannot achieve with metals, with composites, because of such a huge flexibility you have in the capabilities as far as design is concerned. The other is in terms of the ease of fabrication. In fact, now 3D and 4D printers are available for composites commercially also. It was not so just a few years ago. But apart from additive manufacturing, even conventional manufacturing, the availability of composites as raw materials in various form factors makes it suitable for different applications. For example, and also these are over a wide range of costs as well. Some are very cheap but low performing, but good enough for industries such as automotives, especially lower end cars, etc., for passenger cars, etc., or other vehicles on road. But when you go for aerospace, you need much more higher grade, so you have different kinds of raw materials that you work with. So we'll just look at a few of those typically used. One which is very commonly used in the aerospace industry, I already mentioned in passing, is pre-preg, which stands for something that is already pregnated or impregnated. So what does it mean? That you have already put the fibers into the matrix, and therefore you can work with it because it is still in the wet condition. So there are certain storage requirements for pre-pregs under a certain range of temperature and pressure conditions under which they have to be stored, and also there's a certain shelf life for them. You can't use them beyond a certain period of time, and that's different for different composites, etc., different volume fractions also, etc. So that's as far as the pre-pregs are concerned. And typically they will have long fibers, and when we say long fibers, most people are thinking of meters, etc. But the classification is such that even if the fibers are larger than 10 mm in length, it's fairly large, because remember the diameters of these are of the order of 10 microns or so, which is so compared to that, the length is fairly large when you already go for 10 mm. So you can get fairly decent works done. But even longer fibers, especially in the form of toes, which is a bunch of fibers, are typically used when you're dealing with, let's say, filament winding kind of manufacturing, etc. You have to have a continuous supply of the fiber or in the form of a tow. So then you have much longer fibers than this. But purely from a property advantage point of view, as long as this kind of an thumb rule is reached in terms of the total length or average length of the fibers, you get reasonably good properties, and that's a huge advantage that you have. And that itself is a little expensive to make. So if you're looking at situations where you cannot make such long fibers, you come down to about 2.5 mm that you're talking about. So then you're essentially talking about, sorry, that's 25.4, right? 1 inch? Yeah, 25.4. So that's still comparable in terms of the lengths of the fibers, but the form factor in which it comes is very different. These are in the form of sheets, just like you have sheet metal, something like that, but in a much more raw condition, so that you still can do molding with that. So you make certain molds for the different shapes of structures that you want, and you use these sheets and you essentially hammer them into it using fairly advanced techniques, not just hand hammering, and then you end up with a composite part that is made out of it. So these are typically used in the automobile industry, etc., where you can sacrifice a little bit of performance if you can get a cost advantage. Then another one which is even cheaper in terms of for a given quantity for the same kind of materials is the bulk molding compounds. So once again, these are molding compounds like the previous one, but instead of being short, it's much shorter than an inch, and therefore the properties are a little more inferior. So when you make with this, it's much more randomly distributed in terms of the orientation of these fibers, and also there can be some agglomeration taking place, etc. Certain places where the fibers are not at all there, certain spots which can be weak spots, and therefore you have certain issues. But if you are dealing with the manufacture of secondary structures where the loads are not all that stringent, like for example doors, etc., then you can live with that because the margins of safety involved are fairly large, so it's not an issue. And also you have multiple layers, and each layer can have different kinds of agglomeration distributions, so they tend to compensate layer across layer as well. But there's an issue with that. So in terms of the so when you have an appropriate design, you can bring down the thermal expansion as well, because that's something that you tailor. So we're talking about the flexibility in the design capabilities, not only in terms of the overall material properties like stiffness, strength, etc., but in terms of the so-called non-structural properties. But in terms of the loads, it need not always be mechanical, but also the change in temperature, etc., in which case, because of the different coefficients of expansion in different directions for the composites, you can have expansions which change not only the size of the structure but even the shape of the structure a bit, because of the anisotropic nature of the coefficients of thermal expansion. So but nonetheless, overall you see that by an appropriate design you can actually bring down these thermal expansions, and therefore the mismatches may not be that huge an issue. Okay. So let me complete this slide and then we'll break for lunch. So material damping is something that is an advantage. So all the things that we are listing in this slide, remember, are advantages. So in the previous slide we said in spite of, we are talking of all the issues and also ways to resolve that. Now these are advantages. Even in the first column that you saw on the left already, it was all advantage, like for example the low thermal expansion. The other thing is because metals expand or contract much more for the same change in temperature compared to polymers. So the matrix is what drives thermal expansion more than the fibers. Then coming to, because it's also an insulator, so the temperature from the environment is not entirely transferred to the fibers. So if there's let's say a 5-degree increase in the environmental temperature, the temperature increase in the fiber may be just 1 or 2 degrees because of the insulating nature of the polymer, right? So coming to material damping, this is a very important feature. Almost all materials have a certain level of damping which is inbuilt into them because of their very structure, their microstructure that is there, including metals. But the material damping there is much, much smaller compared to polymers, where because of the large chains that these polymers make, the damping is so large that you don't, in many cases, need an external damper as well. The material damping itself is sufficient for that, and that is a huge advantage for a lot of structures subjected to dynamic loads, especially vibratory loads, where just the stiffness of the material is what you bother about, and don't add additional dampers because the material itself can take care of it. Or even if you need to add a damper, the damping requirements are much lesser compared to metallic structures. The other thing that putting three things together is in terms of the resistance to various issues that are encountered through the environment. One is corrosion, fatigue, and third is damage. To all of these, there is a greater resistance in composites compared to metals. Why? For example, let's take corrosion. And again, for a large part in this slide, we are talking of polymer matrix composites, though there are other types of composites. So polymer matrix composites, because the region which is exposed to the environment is essentially the matrix, and polymers are much less susceptible to corrosion than metals. Therefore, the overall resistance of the composite also, even if the fiber is susceptible to corrosion, it is still possible that overall the composite has much lesser susceptibility. Then coming to fatigue, it's a direct translation of your material damping. Because the material damping is large, the fatigue performance is also much better. So if you draw SN curves, for example, you will have the SN curves of the composite a little higher compared to that of metals. The reason being that for a given number of cycles, it can still offer much larger strengths, or in other words, the drop in strength, if you're non-dimensionalizing everything compared to a particular base material that you want to compare with, then you will see that the drop is much lesser in the case of composites compared to this. Again, we're talking in very, very broad terms. There are, of course, differences, and also when you bring in metal matrix composites, things change quite a bit. But otherwise, for most of the polymer matrix composites, that's true. And finally, in terms of the resistance to damage, so once again, this is something that we have discussed in the past as well. When there is a crack in the matrix, and the matrix is surrounded by fibers, so therefore, when you are going to increase the size of the crack because of the increase in the load, it encounters a fiber, and therefore that bridges it and either delays or completely stops or arrests the crack growth. Okay, so slow crack growth. And also you can tailor the so-called fracture toughness, which is essentially the area under the stress strain curve. The more that area, the more it can absorb impact energy, for example. So you can actually make sure that by appropriately designing the volume fractions in each layer, and also the different layers, the direction of fibers, etc., you can tailor the fracture toughness as well, how much of energy it can absorb, right? And because it's anisotropic, properties are different in different directions. The toughness will also be different in different directions, but we know the dominant loading directions. For example, in the wing, we know that a particular direction, a particular panel is going to mainly undergo compression. We know a particular thing is going to undergo only tension or mostly tension. So when we know that a priori, we design it for that. That's what is called tailoring for that particular requirement. And therefore, some areas which are more susceptible to impact, where you try to increase the fracture toughness, where there is no possibility of impact or it's very, very remote, then you try to not play around so much with the fracture toughness, leave it to what it is, focus on the other important priorities over there. And again, damage, it's large for metal matrix composites, because in metal matrix composites, these cracks can grow just like they grow in the case of the metals. So some of these things are holding only for polymer matrix composites, not the other kinds of matrices. The final thing is a non-structural thing, but because many of these are also, as we said, the structure is not only load bearing, but also is the boundary between the environment and the contents of the aircraft. And therefore, things like electrical resistance are important when you're talking about lightning strikes, etc. Heat resistance is important as well in terms of how much of power you require for the internal air conditioning, etc. So some of these things are design parameters as well that you can play around with when you're designing. Once all the structural requirements are taken care of, because that's the primary requirement, then you can play around with these as well to make sure that the energy losses that are involved are as low as possible. So with this, we'll complete today's class and we'll meet next week.